Jai Hind, welcome to class of Analog and Digital Communication. Today we are going to talk about phase shift keying. We know that this is a kind of digital modulation where phase of a very high frequency carrier wave will be altered with respect to the instantaneous value of a message signal. So here the information content will be hidden in the phase of the modulated wave. So at the receiver side, when we receive the wave, we have to read the phase variations, and according to the phase variation, the actual message has to be retrieved, right? So this kind of modulation is called as phase shift keying. It is abbreviated as PSK, and PSK is a digital modulation technique in which phase of the carrier signal is changed by varying the sine and cosine inputs at a particular time. It is widely used for wireless LANs, biometric, contact lens operations along with RFID and Bluetooth communications. If we see our digital TVs as well, there we could easily see that it also uses 16 PSK. So it has many applications in our day-to-day life. So study of PSK is important for us, right? So PSK is of broadly, if we can categorize it as binary phase shift keying and quadrature phase shift keying. Although there are higher versions of PSK as well, which we may study like 8 PSK, 16 PSK and so on. So how do we move to these variations of PSK? Let us take a look at that. First of all, I would like to elaborate about what BPSK is. BPSK is the simplest form of PSK. It is the binary phase shift keying. Here, the phase shift in my modulated wave will be of two variations, like either if we get a phase variation corresponding to bit 0, there will be different kind of phase variation corresponding to bit 1, right? So this is the simplest form of PSK that we are going to study, which is called as binary phase shift keying. We study these shift keying techniques under the topic M array. What does M array modulation means here? Here, my number of variations will depend on number of bits I consider at a time, right? If I consider one symbol is responsible for variation of my wave characteristic. If I consider my one bit is consisting of a symbol, then the number of variations I give by capital M, and which is given by 2 to the power n, where small n defines the number of bit, right? So if in a symbol I consider there is one bit, if because of one bit there is a variation in the characteristic of my wave, then the number of levels, the number of variations that I obtain, considering n equals to 1, my M will be 2 levels. So if I consider one bit at a time, I will have either 0 representation or bit 1, right? So corresponding to these two bits, I'll have some variations in the wave characteristic. Here the wave characteristic that I'm considering is specifically the phase, right? So in its simplest form of variation, my phase shift keying is called as binary phase shift keying because the variation will be of two types, right? M will be 2 here when I consider number of bit at a time equals to 1, right? Whereas QPSK is the next level where I consider 2 bits at a time, right? When my symbol is of 2 bits, that is, if I consider the variation in the phase, the variation in the wave characteristic depends on die bit at a time. If I am going to consider 2 bits at a time, then the number of variation I can assume is, for n equals to 2, my number of levels will be 4. This is clearly visible that if I'm going to take 2 bits at a time, the number of possible combinations I'll get is 0 0, 0 1, 1 0 and 1 1. There are 4 variations or 4 levels that I'm going to get. So in QPSK, the phase variations will be corresponding to die bit at a time, and there will be 4 phase variations, right? I know my quadrant is of 360-degree. If I'm going to divide 360-degree into 2 parts, considering BPSK, then my phase will be either 0 or 0° or 180°. So if I consider corresponding to bit 1, there is no phase variation, that is 0° phase variation. I'll have to consider corresponding to bit 0, there will be 180° phase variation, right? Likewise, in case of QPSK, when I divide my 360 in 4 quadrants, I'll be getting each quadrant of 90° phase variation. That is, my die bit will be varying from next die bit with a phase variation of 90°, right? So these are the bases of classification. That's in brief I've explained for now. So let's start with BPSK in detail. BPSK is also called as phase reversal keying or 2PSK. It is the simplest form of PSK. Here 2 phases are useful, which has 180 degrees separation, and these 2 phases are represented by either bit 0 or bit 1, where bit 0 represents 0 degrees phase shift and bit 1 represents 180-degree phase shift, or vice versa could be the case, right? In this method, certain basic functions are selected. The position of the constellation points on the wave does not matter. They can be placed anywhere, right? Corresponding to bit 1, if I am representing 180-degree phase shift, corresponding to bit 0, I have to represent 0°, right? It is the best form of PSK as it can take care of huge noise distortion, right? If there is some error because of noise, then the noise has to be powerful enough to cause a phase variation of 180°. Then only bits can be misread, right? 1 could be read as 0 only when the noise will be powerful enough to make a phase variation of 180°, so that my receiver misread the bit, right? So this is very much noise resilient. One major disadvantage, however, the disadvantage of PSK is that it can only modulate 1 bit per symbol. So the information carrying capacity of BPSK would be quite lower, right? Because of 1 phase variation, I am sending just 1 bit. Whereas if you consider the case of QPSK, with a single phase variation, we are transmitting 2 bits, that is double the amount of BPSK. And likewise for HPSK, I'll be sending 3 bits per phase variation, right? So although the phase variations are reducing at higher levels, which is increasing the receiver complexity, which is required to differentiate the die bits or tri bits, and there could be possibility of error because of noise introduced. When there will be noise introduced and there will be little phase variation, because of the already existing lower phase variation, the noise can cause the die bit or the tri bit could be read as wrong bits, right? So that increases the complexity of my receiver. However, the information carrying capacity increases by increasing the value of n, right? When I increase the value of n from 1 to 2 to 3, the number of bits per phase variation will increase. I hope I made the point clear. So this represents, if corresponding to bit 0, I represent phase in this direction, corresponding to bit 0 here, 180°. If I want to draw the waveform for PSK, let's see. I consider my binary bits like bit 1, 0, 1, and let us consider that in 1 bit duration my 2 carrier cycles are passing. If I consider corresponding to bit 1 there is 0 degree phase shift, and corresponding to bit 0 there is 180 degree phase shift, the modulated waveform for BPSK would be, for bit 1 there is no phase shift, so the carrier wave will start like this only. For bit 0, however, for bit 0 my carrier would observe a phase deviation, a phase variation of 180 degree. So if I see my carrier was starting from here, in the resultant wave it would start from here, right? So that makes a phase reversal of 180 degree, right? And in case of bit 1 my carrier will remain as it is. So however, it looks like a phase variation, but it isn't a phase variation, right? So this, when at receiver, my modulated wave will be compared with the carrier. These phase variations will give the prediction what was the bit that was sent actually, right? So when these two will be compared, from this phase variation, it will be easily read that the previous bit was bit 0, but here the previous was bit 1, and here the bit is 0 because of the phase variation observed here, right? So my receiver will retrieve back the bits from the by reading the phase variations of the modulated waveform. This is how I can draw the waveform for BPSK. Let's see how do we generate BPSK. Now the idea is clear. One of the input is my message signal, another input is my carrier wave, and because of the presence of my bits and a high frequency carrier wave, what do I get in resultant is a modulated wave with phase variations, which will be carrying the information what the original bit was, right? So this gives me an idea that we do need, of course, a product modulator, because to a product modulator there will be two inputs. One of the inputs will be my binary data sequence, which I have represented with BT, right? The another input should be my carrier wave, which is represented here like this, right? This is the energy associated with my carrier. So cos 2 pi FCT represents the angle of my wave, where TB represents my bit duration, right? Although we are not going to give the bits directly to the product modulator, we are going to give it through a polar non-return to zero level encoder. What it is going to do? Because I do not want my carrier wave to be directly getting multiplied with the bits. What do I want is, when I'm passing bit 0, it should be multiplied with negative value, and when I'm passing bit 1, it should be multiplied with a positive value, and the amplitude of the carrier must remain same. In the modulated waveform, the amplitude must be similar to that of the carrier, right? So whenever I'm passing bit 0, it is going to raise the level to some negative value, and for bit 1, positive, right? And when it is going to pass through the product modulator, what do I get is a binary PSK signal. The block diagram of BPSK consists of a balanced modulator, which has carrier sign as one input and binary sequence as the other input. right? The modulation of BPSK is done using a balanced modulator which multiplies these two input. For a 0 binary input, the phase will be 0 degree, and for a high input, the phase reversal is of 180 degree. Although the case I have considered is opposite of it, you can consider either of these cases. Like for bit 0, you may consider no phase change, and for bit 1, you may consider 180 degree, or vice versa, right? The output sine wave of the modulator will be direct input carrier or the inverted 180 degree phase shifted input carrier, which is a function of the data signal, right? So this is the waveform. This is the diagrammatic representation of BPSK modulated output wave along with its given input. This is the binary input which we give, right? So what we are going to observe is for bit 1 there is no phase change, and for bit 0 there is 180 degree phase reversal. For bit 1 no phase change, for bit 0 there is 180 degree phase reversal, right? This is how I may represent my BPSK modulated output waveform. Now let's talk about the receiver part. At receiver, how demodulation takes place. Now the block diagram of BPSK modulator consists of a mixer with local oscillator circuit and a bandpass filter and 2 input detector circuit. Whereas it can be simplified by representing it with the help of a correlator and a decision device, right? This is how I'm going to get my modulated waveform, which we usually represent by ST, and here I'm going to use, as this is a coherent kind of detection, I'm going to use here exactly similar carrier which was used at transmitter, right? So my modulated wave and my carrier gets multiplied at the product modulator, right? And this goes up to all the bits, right? For all the bits that was used at transmitter. Now this goes to a decision device, and here we do provide a threshold. Like if in case for bit 1 plus 5 volt was used at transmitter, and for bit 0 let's suppose 0 volt was considered, then I might use a threshold value of let's suppose 3 volt, right? Anything higher than 3 volt would be considered as bit 1, and anything lower than 3 volt would be considered as bit 0. So that is the role of this threshold use here, because this plus 5 volt might get reduced to 3 volt in case of noise, and 0 might get increased to 0.5 volt, 0.2 volt or 1 volt, 1.5 volt because of the presence of noise. But as long as it is lower than 3 volt, we will read it as bit 0. Now decision device will read the values and will give its decision whether it has to be interpreted as bit 0 or bit 1. By recovering the band limited message signal with the help of a mixer circuit and bandpass filter, the first stage of the demodulation gets completed. Now as the baseband signal is band limited and its obtained signal is used to regenerate the binary message stream, so in the next stage of demodulation, bit clock rate is needed. When do we need the decision? We need the decision at every bit duration. This sampling switch, this switch get closed at every TB, right? So a clock is needed here. When to take decision? After every bit duration, so that we predict exactly similar number of bits. Otherwise it will give continuous bits, right? So we need a clock here. Is needed at the detector circuit to produce the original binary message signal. If the bit rate is a submultiple of the carrier frequency, then the bit clock regeneration is simplified. Now to make the circuit easily understandable, a decision making circuit may also be inserted at the second stage, which is the major task of the demodulator circuit. So this is how we demodulate a BPSK signal. Just to revise, input, modulated signal, carrier is given to the product modulator. What we get must be passed to decision device at every TB bit duration, and it will decide, reading like comparing it with the threshold. If it is higher than the threshold value, bit 1, if lower than the, then bit 0, right? So these are few applications which I have discussed previously as well. It is used for satellite TV, WiMAX, WLAN, CDMA, right? It is considered to be a robust kind of system of all the modulation available. It is used in OFDM and OFDMA. Also, the channels are used for specific data transmission in cellular systems. The channel used to transmit system-related informations, which are very essential. They modulated using BPSK modulation. So this is widely used in our day-to-day life. These are the references I have used. Thank you.